The importance of this table is basically saying because this is a community college, which has no entry requirement, zero. So that means anyone can come in here and take CISP 300 as the first class in computer science. So when it comes to the um, general student population in CISP 300, it'll be at exactly 50th percentile. Does that make sense? But in order for a person to be successful in the long run in computer science, they need to get up to at least, okay, let's not look at those numbers. Let's look at these 75, 75, 80, 65, and 60th percentile. So the question now is if somebody starts at 50 percentile, how do we bring those people up to, you know, the target percentile? Is that making any sense? So the next one has to do with what is innate and versus what you can learn from education. Okay, this is just a table. So I would pick a particular role. Let's talk about technical precision. Okay, how well do you know the syntax of C++ or the API of a particular thing that you need to access and so on and so forth? How many people are born knowing the syntax of C++? No one. Everybody learned that. Okay, so that's basically one example of something that, well, we are not really born with that. Everything is learned. So the only thing that is a little bit of an innate nature is abstraction capacity. The ability to see patterns is more innate. It doesn't mean that people who are average cannot gain the ability. It's just not as significantly as the other ones. It can still be gained, but it really takes some hard work on the individual's part. Okay, but everything else is not set, okay, in stone. Everything else can be acquired by a large degree. Is that okay? All right. And then the last one, this is part five, which is the last part. It is the most important one, which is how do we get there? Okay, how do we improve for each dimension, what we can do, and there's an example of how to do it. So that's basically what this document is about. If you guys are interested, I can send it as an announcement. If you're not interested, it's just what we just mentioned earlier. That's all. All right. Are we good with this? Any questions? No questions. Okay, cool. And then in my CISP 300 class, I also talked about note-taking tools. So this is a web page, with a bunch of, open source or otherwise, note-taking tools. Um, I had to mention this in my CISP 300 class because many people were not taking notes at all, as in coming in with nothing at all except for a phone. So that may not work out in the long run. So I have to remind people of, okay, you might need to take notes. Zerno++ is one of the tools that's missing from this list, which I find to be quite useful. If you have a computer that is capable of using a stylus, so you can write on the screen, Zerno can let you capture notes just using your laptop computer. I think my son uses Zerno for taking notes in his classes, especially in the class where you have to draw diagrams and whatnot. You cannot just type everything. All right, so that's that. And now we can move back into the actual content of this class. The first assignment, or not first, the just functions assignment is due now. Are there any questions about this? Or do you guys go like, okay, we got it, no need to talk about it? Which way? Yes. Okay. Specifically, question number four. Okay. So, uh, okay, so we can go for Preview. There we go. This is what I want. Well, since we're going to get to question number one, we might as well do the other ones too. So question number one should be relatively easy because it's asking for the Cartesian product between the two. So you're going to be A1, A2, A3, B1, B2, oops, B3, oops, B3. So that would be a totally acceptable answer for this question. Question number two asks you about the cardinality of what you end up with in question number one. So if you do all the counting, that would be six. Question number three asks you to enumerate the enumerate sets that can be considered functions using x as a domain and y as a codomain. So how many of those do we have? That should be, let me see, 2 times 2 times 2. That should be 8 of them. Okay. So now you ask, how? How can we know that there are exactly 8 of them? Because every function has this template. Okay. So A has to map to something, B has to map to something, and C also has to map to something. So every single function is going to look like this. Does that make sense? Oh, there's no C? Then it won't be 8. There will be It will be 9 because there are three choices for whatever A can be associated with, and then for each one of those, B can be associated with one of the three as well. So that's why we have 3 times 3, which is 9. Does that make sense? Okay. So this one, if you are kind of tired of doing this manually and you can write a program faster than you can type 9 lines like this, use a program to do it. How many people would use a program to do this part? Yep. It'll be a good programming exercise. It's a double loop. The first loop iterates through A and B, and then the inner loop iterates through 1 to 2, and then you just do a printf or cout, print out the whole thing, and copy and paste it from your command line interface, and you're all done. So most people in this class should be able to write a program to do this. I would say within 15 minutes at the most. Okay. Um, So, do you want me to do this or actually just kind of, okay, Tech, I think we know how to do this. You go further? Like the answer to this question? Okay. So I am going to write a program to do it because I said, it will be doable using a program. So I'm just going to do it. Um, and I'll put my IDE here. This is how I write programs. I use the command line. So go to my temp folder and we'll just say cross product. So just click cross. This is straight C, not even C++. So I need some outputs. So include this, and then we have AB, right? So we have char um, lowercase x, and then we have int y. 4x equals to initialize it to lowercase a. It has to be less than or equal to b. I use the wrong punctuation here. Plus x increment. And then we can do something for y2. Y start with a 0. Y is less than or equal to the last value, which is a 2. And then plus y. I don't really need the braces here, so get rid of those just to make it harder to read. And then now we can specify the printf. It's going to go to a few places. Actually, no, I take it back. Okay, let me see where I need to. Mm, Okay. So we need the open X. Okay. Oh, okay. I see. That is the problem. Okay. So I need to do one printf here. So that means I need to use block statements after all. Okay. Okay. Because I need to print here what x is for now. So this is the beginning of a tuple. Oh, that won't work either. Hmm. Hmm. Initialize the array. Well, we know it involves two loops because we know one loop is going to loop through the three choices here, and then for each iteration of the loop of that loop, we also can go through all the possibilities over here. So the double nested loop structure is correct. Um, but we also need to print out this format. Oh, okay, I know what to do. Okay, now I get it. Um, right. So okay, so I used the wrong words here. So I really should be using variable A and variable B, and both of those are integers. So now we have A going from 0, A is less than or equal to 2, plus A. So that would be the top level code, which is responsible for what A is mapping to. And then B is going to be the second level. So B, or what B is mapping to, is going to be the responsibility of the inner loop. Um, and the printing is going to be at the most nested level, which is here. And that would be printing the entire thing. Okay, so it's going to be open brace, open here, A is mapped to the variable A or whatever value is in A. So %d in printf as a format string refers to the first integer that is after the format string itself, and then B would map to whatever the other integer is, and then close here line feed, and then we have A, B as additional parameters to the printf, and that should do it. I was over complicating it originally. All right, so we'll give it a try. Okay, gcc-g-o cross.c. Well, it compiled just fine. Run it. There we go. So, any questions about this? Did anyone do something like this? Perhaps in a different language? Okay. All right. So, with that said, I'm going to. Are you in my class? This is CISP 440. Are you in CISP 440? Because the previous class ended about half an hour ago. The math 373 class ended about 30 minutes ago. Yep. Not that I mind you being here, but I just wanted to check with you. All right. Yes. Set format. Um, the yes, you can. You can use the notation that we use to define Cartesian product itself, but that's not what the question is asking. Yeah, so the answer to your question is yes, we can use a notation instead of spelling out everything, but the question is asking you to spell out everything, so you cannot use a general description. Yeah, because the question specifically asks, use one line for each set that can be considered a function using X as a domain and Y as a codomain. So you do have to spell them out. Okay. All right. So question number 4, which is the whole reason why we are going through this. Okay, based on how X and Y are defined in the earlier question, being question number 1 in this case, how many subsets of X Cartesian product with Y are not functions? In other words, you have to use everything that is not in part 3. Okay, we're looking at the subtraction of the what we call a power set of the Cartesian product, and then we subtract the answer of question number 3 from the power set, and that would become the answer. Okay, so the question or the format, and then they will ask you. Oh, it only asks about the cardinality, so that's a lot easier, because otherwise, I would have to spend a lot of time to actually kind of print out all the subsets. Yes. So you can look at the structure of the whole thing. We are looking for the cardinality of a set. So what is a member of that set? Every member of the set F is a subset of the Cartesian product between x and y, and it is not the case that F is a function that maps from x as a domain to y as a codomain. So that's how I would read it. So now the first question is, how many subsets do we have of the Cartesian product between x and y? So before we answer that specific question, the follow-up question is, if I just give you a set of 6 elements, okay, A, B, C, D, E, F, how many subsets can I generate? In other words, how many subsets does the set of A, B, C, D, E, F have? That is correct. Yes, go ahead. Oh, you're about to say that? Okay, but why? Hmm? Yeah, come on now. Yep. And I'll try to find you a dry board marker. Okay, there's a reason why the math professor has its own, because there's none that I can find. Mm, I'm sorry, but we cannot find any dry board markers anywhere in this room. See if there are any over there. Nope, there's only an eraser, no markers. Hmm, that's all right. Hmm? Okay, thank you, Anna. Because I was about to set up the tablet so that we can use the tablet to do some writing. Right. So that's the Cartesian product one. Hmm. Hmm. But why? Why do you raise 2 to the power of 6? Why is the cardinality of this the power that you use? That was the original question. Why are you using 2 to the power of 6? Why use power 2? Why is it raised to the power of 2? Okay. All right. Well, do you mind if I Yep, go ahead. I don't think it is as related to Pascal's triangle. We will get to Pascal's triangle, by the way, in this class, but I don't think it is as related to Pascal's triangle. Yeah, because, okay, okay, can you repeat the question? What is not a proper subset? It is a valid subset, but it is not a function. But we are not even there yet, okay? We are trying to list all the functions for the time being. Okay, so let me see if my router is up. Okay, and so now I can use my tablet. All right, so this will take a little bit of time too because it's not connected yet. Mm, 440. Okay. And this part I really need to draw because I think this is a technique that can be useful for many other discussions, and that's why I really wanted to use a graphical representation. And so now I think it's ready to go. Yep. Okay. So I'll do the supernote. That's okay. It's mm, all right. Let's try it one more time. Okay, it's not working because my tablet is not connected to the same network. Give me a second to Wi-Fi. Nope. Uh, nope. Hmm. I am. All right. That is strange. All right. Well, may I borrow your dry board marker? Because I have some networking issues with my router. It won't make the connection. Thank you. All right. So the way I think about it is don't even think about these are tuples. Just think of those as 6 elements, A, B, C, D, E, F. Okay. So the question is, if I have a set that contains A, B, C, D, E, F, how many subsets can I generate out of that set? That is the question, right? So the way I look at this is a decision tree, or not a decision tree, it is just a binary tree. This one is about A. It's either A is there or A is not there. Okay, that's A. And then for each configuration of whether A is there or not, when I look at B, B can be there or not there. B can be there or not there. Okay, and then I'll do another level before I use up all the ink in the dry marker. So when we get to the C level, it's the same thing. There, not there, there, not there, there, not there, there, not there. In other words, every time we add an element into consideration, we are doubling the total number of leaf nodes because A can be present or absent, B can be present or absent when A is present, B can also be absent or present when A is absent. So that's how we generate a binary tree. Every time we add an element, we are doubling the number of branches. So by the time we get to the sixth element, we would have 2 to the power of 6 branches. Yes. Mm-hmm. Yep. 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 The other, there's one more way to look at this. If you're familiar with binary numbers already, think of a 6-digit binary number, a 6-bit number. And in each bit position is corresponding to the presence or the absence of an element. So that's the other way to look at this. So that means the binary number 0000000 means an empty set. No one is there. The binary number of 111 is the original set, which means everybody is there. So now you have to think about how many different binary numbers can you have when you have 6 digits. The answer is 2 to the power of 6, 64. Okay, so that's how we can come up with the answer of 64. So now getting back to your homework. Okay, uh, there we go. So that means this part here is giving you 64. But out of the 64, we want to rule out the ones that are actually functions because this the part here which says not a function. So we already know there are exactly 9 that are functions. Okay, so once you subtract 9 from 64, then you get 55. So the answer to this particular part is 55. Is that okay? All right. So that's how we kind of answer all of these questions. All right. So getting back to today's lecture. So today's lecture is moving on to talk about the properties of a function. So we are not really talking about just functions anymore. So from today's lecture content, which I think we have enough time to go over everything, you will also have a homework assignment due in a week. It is called function assignment, but we'll be focusing on injection, surjection, and bijection. So there we go. So this is about injection, surjection, and bijection. So we'll start with injection. Yeah, no, but you would not. You need to learn how to read it. Yes, yes, yep, yep. You need to know how to interpret it. Mm, yes. Not yet. Because I think it's important to know how to read it first. Okay. So does that answer your question? Okay. So now we are talking about injection. So an injective function, also known as an injection, has each element of the domain mapped to a unique element in the codomain. So this is the key part, right? This is the verbal definition of what an injection is. First of all, it has to be a function, which means if you have a subset of the Cartesian product between x and y, but that subset is not even a function, forget about whether it's an injection or not. We don't talk about injection unless that particular subset is already a function. Okay, so this is on top of being a function. So now the question is, but what do you mean by each element of the domain maps to a unique element in the codomain? So let's go ahead and step by step construct the notation that that I have already derived. So every time you see the word each, okay, each blah 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 and so on, it is a strong suggestion that you have to use the universal quantifier, because whenever we use the word each as opposed to there's at least one, okay, each implies that whatever that follows here has to be true for every single element, whatever whatever the set is. So in this case, we are looking at each element of the domain, which typically I use X to represent. So that means, oh, we better check and make sure that every element in X also meets the requirement that is following. Is that okay? So what requirement are we talking about? It has to map to a unique element in the codomain. So that means you cannot have two elements from the domain mapping to the same element in the codomain. That is what it means. Okay? But verbal definition is always a little fuzzy. It's always a little bit vague. So that means, when we want to express it using the notation, this is what it is going to look like. Okay? So the way it is described is for every p in x, okay, once you have fixed what p is, then you say for every q in x. So can p and q be the same? Yeah, they can be the same because you have basically a double loop to loop through every single possible element in X. Okay, so there are chances that P and Q are the same. It's okay, it's not a problem. So now what about P and Q then? Okay, what do we need to qualify P and Q? This part here is what qualifies what needs to be true in this case, but for every possible way to pair up P and Q. So that means, so what this says is if P does not equal to Q, it implies blah, blah, blah. Okay? I'm going to forget about blah, blah, blah first. And you ask, but what if P and Q are in fact the same? Well, if P and Q are the same, what happens to the expression P does not equal to Q? It is false. Okay? So what happens when the left-hand side of implication is false? What happens to the implication itself? The implication itself is true from the truth table. Okay, so this is why in week one, on the first day, we talked about Boolean operators. This is also why I use a truth table. So this way you don't have to interpret what implication means. You have a table to look up. Okay, if the left hand side is false, the implication itself is true. Oh, so that means when P and Q are the same, we don't have to worry about that because in a universal quantifier, we want for every way to pair up P and Q, we need this to be true. So when P and Q are the same, I don't even have to worry about anything because by default, it is already true. So what if P and Q in fact are not the same? Well, then you have this expression being true, which means the value of the implication now depends solely on the right-hand side. So on the right-hand side, we have f as a function applied to p, we have f as a function applied to q, and we say, oh, they have to be different. So this means for every element p and q that are different from the domain, after you apply the function, the value after the application of the function also have to be different. So is that okay? Are we understanding how to interpret this particular statement? Yep. Okay, right, the right side of what? Okay, so you're talking about P does not equal to Q. So what about it? Are you talking about this one? Huh? The arrow. You mean this one here? Oh, the right side. Sorry, okay. That's what you said. I just misheard it. There we go. Okay, the right hand side. What about it? No. When you apply f as a function on P, and when you apply the function on Q, what they map to, because f of P is what P maps to, f of Q is what Q maps to by f. So they what they map to cannot be the same. Yep. So this is basically defining what uniqueness means. Yep. I will go with you and then okay. Are you first? Oh, okay. Because you can see him, but he cannot see you. Okay, go ahead. Yeah. Yes. But they have to be not exactly. It means P, what P maps to cannot be the same as what Q maps to. We know that P and Q they must map to something in Y because otherwise F would not be a function. No. P and Q are both coming from no P and Q are both coming from X. We're looking at what they map to and say that if P and Q are coming from the domain and they're different, then whatever they map to in the codomain, they need to be different. Yes. Okay. You can look at it from the graphical perspective, but in this class, we usually do not work with actual functions. So what we can do is I can give you an example. Okay, so I think this is good. Okay, we can talk about an example. So the example I'm going to give you is um, this is an injection. So I'll give you an injection example. So in this case, f is already known as a function mapping from x to y, but instead of using x, I will tell you exactly what x is. We'll just have a simple one because I don't want to waste too much time on this. So we have 0 and 1 as the domain, and then y is going to be a and b, okay, just so that it's easy to tell which one is from the domain, which one is from the codomain. So the function of 0 a, let's kind of move things up a little bit. This is a function. It's a function because each element of the domain maps to one and only one element in the codomain. So it is a function, but is it an injection? So the way you test whether this is an injection is to say, okay, so remember the P and the Q? So P can equal to 0. P can also equal to 1, right? Because those are the only two available elements from the domain, which is X. But when P is 0, Q can also be either a 0 or a 1. Does that make sense? So you're basically looking at you're looking at a double loop or a nested loop. Same thing over here. Are we okay so far? So for each one, okay, so this is representing when P is 0, Y is, excuse me, when P is 0, Q is also 0. So now we want to evaluate the second part of the expression. So let me go back to, okay, we'll shrink this as much as we can. And then we go back and look at this. Okay, we look at this whole thing here. So we look at that particular expression. So that would be true in this case, right? This part of the expression, P does not equal to Q implies blah, 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 because they are the same. If they are the same, then P does not equal to Y is false. When you have a false on the left-hand side of an implication, the implication is already true. So that's why I put the true here. Is that okay? Hmm? This is a part of determining whether F is an injection or not. We have no conclusion yet. Well, okay, I'll refine my answer. We cannot rule out the possibility that this is an injection. We have no evidence that this is not an injection yet. Yep. Yes. Yep. So I can also say something like this. P does not equal to Q implies F of P does not equal to F of Q is true. Okay? And this is true only because of the first part of the implication, because P and Q are the same. Yes. So I'm going through the tedious process to make sure that they are all true. Okay. So now we have P equals to 0, Q equals to 1. P does not equal to Q is true, right? So that means I cannot conclude yet about the implication. So now I have to go to the the right hand side of the implication and ask, okay, fine, what is F of P? So F of 0 is B. Okay. What is F of Q? That is A. B does not equal to A is, come on, you guys know the answer. B does not equal to A is true. Okay, so now we have true implies true, which is also true. Yep. Okay, so now we work this out. So I'm just going to be super duper lazy, just copy and paste because that's the conclusion. Now we work with the third case. When P is 1 and Q is 0, what happens to P does not equal to Q? It is true. So now we have to look at the second part, right? So now we are looking at f of 1. F of 1 is a A compared to f of q, which is f of 0, which is a B. A does not equal to B is also true. So now we have true implies true again. So now, that's what that's why I just copy and paste it, because and this one is also going to be true, but it's an easy true because P and Q are exactly the same. So P does not equal to Q is false. The left-hand side of implication is false means the implication itself is true. So I can already come to the conclusion that it is true as well. So once we have all of this figured out, then we look at the conclusion here. Okay, that's true. This is true. This is true. This is true. So for every possible way of getting a value to P, getting a value of for Q, this whole expression turns out to be true. So now the universally quantified expression is true, which means now we can conclusively say that this particular function is an injection. It is injective. Yep, correct. So if you want to see it as an example like this, but in a different way, so now we can copy and I can also save the file and then just kind of send it to you guys. Huh? The recorder is on. Yes. Yeah. Yep. All right. So now we paste it, and this time we go like, okay, we're gonna use the same domain and the same codomain, except I switch things around a little bit and turn it this way. So now the question is, which one is going to be false? What do you think? One and only one of them becomes false. The question is, which one? So we know the P and the Q being the same is trivial, okay? So we don't worry about this one. We also do not worry about this one over here. So let me use the mouse pointer so when you watch it, it makes sense. Because P and Q are the same over here. So this one is like, it's a constant, we know that. This one is also a constant because P and Q are both ones in this case. So it has to be either this one becoming a false or this one becoming a false. Question is, which one? Well, we'll try that out, right? The answer is both of them become false. They are both false. Okay, so why are they both false? Just plug in the 0 and 1 and figure it out. Okay, in other words, you have to do your part to work it out in order to say, oh, I can see why it is false now. Okay, so let's take this one. I'm going to highlight the one that I want to work on. So let's take this one into consideration. Why is this going to be false? P is a 0, Q is a 1. Okay, P 0 does not equal to 1 is true. Okay, so that means I cannot make any conclusion yet about the implication. So what is f of 0? F of 0 is A. What is f of q? It is also A. A does not equal to A is okay. Let's finish this and then I'll address your question. A does not equal to A is false. So now we have true implies false, which means the implication is false. Oh, so we make a false over here. That is why. Okay, let me address your question now. So in the exam, I typically would have 3 and 3 or 2 and 3, that sort of order of magnitude. So it would still be something that you can eyeball. You write a program to do it. That's what I would do. Um, but it is a very okay. So let me. I did not say. I'm not saying this as a challenge, but I'm gonna say it because I'm curious. So what else? How else are you going to define a one-to-one correspondence? It is about the precision. Okay. So in people have the ability to look at a few examples and generalize. That's once we go back to the abstraction that we talked about earlier, and then we kind of like, okay, we have a general understanding, but is that general understanding really precisely described? Maybe not, right? So that's why I personally like to use notations like this to define what does it mean to be injective. Yes, but we don't want to have redundancy. Having redundancy. hmm Okay, but there's another reason why I choose to use this notation, because the code to check whether a set or a function is injective or not is already here. This is the outer loop, this is the inner loop, this is what you need to evaluate for every single iteration of the inner loop. Whatever answer it gives you, just make a gigantic and the result of the and is the answer to the entire quantified expression. So the mathematical notation is already the logic to check it. Question? Unique element from the Y. Yes. But this is exactly why I use this notation. Okay? Because interpretation using a natural language can be fuzzy and vague, but the notation is not vague. The notation is pretty rigid. It cannot be vague. Yep. So I would go back to the definition. Every time you have a question of whether it is or not injective, go back to the definition, go through the same kind of logic here, check every single case, and to be correct here, this is also a false because it is um, commutative in this case. Hmm? Not exactly. So the discrete part comes from the fact that we are using the kind of the kind of values that we put into a set is called at the worst it is countably infinite as opposed to uncountably infinite. So anything that is countably infinite is called discrete. That's the term discrete has a very specific meaning in math. So you can now tell your calculus professor, so what I'm learning in CISP 440 is discrete, so that will make your math indiscrete. And watch the reaction from the math professor. Not discrete, right? It's indiscrete, but indiscrete has other connotations. Um, anyhow, well, but this is the other way to say it. So the other way to say that F is an injection is to look at this expression here and say that, oh, okay, if this expression, the entire quantified expression is true, then we can also claim that F is an injection. So now we take a look at this one and see how it is doing the same thing, how it's describing injection, but in a different way. So this one only has one quantified or quantifier, okay, because it only says for each element Q in Y, this whole thing in parentheses should be true. Is that okay? So what is that whole thing? Okay. So you look at this whole thing and go like, okay, so the last operation of this whole thing is some number has to be less than or equal to 1. You get that part. It's just comparison. But what number are we talking about? It is the cardinality of a particular set. Okay. So what is in that set? That set has elements that are two tuples. The Q is already fixed by the outer quantifier, but the P is free. So that this is basically saying, okay, find me all the elements of F that ends with Q as the second item of the two tuple. That's what it's asking. And then we want to count how many of them we do, make sure it is less than or equal to 1. So as long as this whole thing is true for every element Q in Y, then we know that F is also an injection. All right. Shall we look at it this way and use the example? Let's do that. Okay. So we are going to go back to the mouse pad and use this other way of looking at things. So we'll start with the one that we worked out earlier. Okay. So in this case, only Q is affected by the quantifier. So Q can be a 0. Q can be, oh, no, I take it back because it is from the codomain. So Q can be A, Q can also be B. Are we good so far? So when Q is A, then we are looking at a set that we're constructing. So let me scroll up a little bit so you can see the function f itself, or I can make the screen a little bit longer. Well, that works better. Okay, so the function f is defined here. Okay, this is f as a set. Okay, so let's put it here. So now tell me which how tell me all the elements. Okay, all the elements of f that where the second item is an A. Which one is it? Look at all the elements of F. Tell me all the elements of F where the second item of the two tuple is A. Okay, that's the only one, right? Okay, 1A. That's it all. That's all we can put in here. So now we are asking this question. So is it true or not? It is true. Okay. Now we look at the other one. Okay. We are looking at the cardinality of a set where the second item is ending with is a B, but it has to be an element in F. So can someone find me all the elements in F that ends with B as the second item of the two tuple? It's 0B, and there's only one, right? Okay. So the question now is the cardinality of this particular set less than or equal to 1? Okay. So now we have shown that for every element in the codomain, being A and B, the quantified or the expression that is expressed, I need to move the editor out of the way to see that. So now we can see that this part here is true no matter which element you choose from Y. So that means the quantified expression as a whole is also true. So this is the other way to look at things. Sorry, you like this one better? Most people would say the first one is actually easier to understand, but okay, well, if it works out for you, it works out for you. Okay, so now we're going to work on the second example. Okay, so I'm going to scroll the screen here a little bit. Okay, and so this time f is redefined to be like this. This is our second example. So now I need to ask you which one is true and which one is not true. Okay, and why it is not true. Okay, because there are two reasons why it is. Well, actually, I take it back. Yep, go ahead. That is, you are correct. But the second one is not much better because in this case, we would have two elements here, right? Because 0A is also in F and it also ends with A as the second item of the two tuple. So that means we have a cardinality of 2. 2 is less than or equal to 0, but less than or equal to 1 is false. What about B? Well, okay, I take it back. This one is true, but the second one, excuse me, this is false because 2 is less than or equal to 1 is false. But the second one is actually true because in this case, it's an empty set. Yes, you can make a conclusion, but I do want to point out the second one is still true because an empty set has no elements, so the cardinality of an empty set is a 0. 0 is less than or equal to 1 is true. So the importance of the second one is for a special, for I shouldn't say special case, it's for cases where you have something like this. F is already known as a function mapping from 0, 1, okay, again, to a set of A, B, C. Ah, okay. So this time is a little bit trickier, right? So F is also known as a set to map from 0 to A and then 1 to C because that's all you can do. So B is not mapped to. Is it still an injection? It is still an injection because we are looking at things from the perspective of the codomain. We are asking, hey, member A of the codomain, how many people are mapping to you? Only one? Okay, one is less than or equal to one. We good. What about element B? How many things from the domain are mapping to you? You go like, no one is mapping to me. Zero. Zero is less than or equal to one? True. Look at C. How many things are mapping to you, C, member C of the codomain? Only one person is mapping to me from the domain. One is less than or equal to one. We are good. Okay? So that's why the example of B in the previous one is important because we have to say, okay, what if something in the codomain is not mapped to? It's like, it's okay, not a problem. Okay? All right, so we are now moving on to surjection. Okay, so surjection, moving on to surjection. So a surjection is a function to begin with. So if something is not a function, don't even ask whether it's a surjection or not. So a surjection is a function where every element in the codomain is mapped to. Okay, so this is one way to define it. This is the other way to define it. You go like, wait, Tech, isn't that the same thing that we looked at earlier? Almost, okay? Where we had less than or equal to, this is greater than or equal to, okay? So now we can now say, okay, exactly what is a surjection? Okay, give us some examples. So let's take a look at the first example, which is this one here. Is that a surjection? Yep, It is a surjection because when you look at it from the perspective of each element in the codomain, you ask, hey, element A in the codomain, how many things map to you? Only one thing because one maps to me. Is one greater than or equal to one? Yes. And then you ask, hey, member B, how many things map to you? Oh, there's only one thing in the domain that maps to me. Is one greater than or equal to one? Yes. So this function f is both an injection and a surjection. So when a function is both, it is also called a bijection. Okay. What about the second one? Look at this guy here. Is that a surjection? So once again, we ask the questions. Member A, how many things map to you? And member A says, oh, there are two things mapping to me from the domain. 0 maps to me and 1 also maps to me. So is 2 greater than or equal to 1? We're all good. You move on to member B and you ask, hey, member B, how many things map to you? Nothing maps to B. So that means the number of things that map to B is 0. Is 0 greater than or equal to 1? Nope. Okay, well, since there's one thing that replies with a no, that means this particular function is not a surjection. It is it is also not an injection. It is neither an injection nor a surjection. Are we good so far? Sorry? It is not a surjection. I just explained it. How many things map to B? And 0 is not greater than or equal to 1. Yep. All right. So let's take a look at the third one. Okay. So if I don't even tell you what maps to what on the third one, we just say, okay, we know that domain has 2 elements, the codomain has 3 elements. We already know it cannot possibly be a surjection because there are not enough things in the domain to go around. This is also called the pigeonhole principle, which we will also talk about later. But this one cannot possibly be a surjection. Okay, so let's look at some other really kind of deformed functions, which means they are really kind of odd, but we can still talk about them. Okay, f is known to be a function. 0, 1 is the domain, and a by itself is the only element in the codomain. Okay, I can tell you right away, there's only one function. F only has one choice because it has to map both 0 to 1 and 1 to A, and it is also guaranteed a surjection. There's no other way to do it. So this one is guaranteed a surjection. Okay, so now we can look at some other ones. Okay, let's say that F has 0, 1, 2, and the domain has 0, 1, 2, and the codomain has AB. So with this one, I can guarantee one thing without even knowing the membership of F. It cannot be an injection. There are not enough things in the codomain to go around. Okay. In other words, one of the two things in the domain has to map to the same thing in the codomain. Now, which two map to which one in the codomain? I cannot tell without knowing the actual membership of F, but I know it has to be true. There's just not enough stuff to go around. Okay. But is it a surjection? Now that I also do not know for sure, okay? Because all 3 elements in the codomain, in the domain can map to one thing in the codomain, making it not a surjection. So just because the domain has more elements than the codomain means that you know for sure it is not an injection, but you cannot conclude that it is either a surjection or not a surjection. You have to look at the actual membership to find out. Yes. they cannot all be unique because you have three things in the domain to begin with, but you only have two things in the codomain. So that means there are not enough elements in the codomain in order for the function to be injective. Does that make sense? Okay, for the surge action, we don't know for sure. Until I see the membership, I cannot tell. No, I said I cannot tell whether it's a surjection or not. So I can give you an example where it is a surjection. So 0 maps to A, 1 maps to A, and then 2 maps to B. It is a function. It is not injective, but it is surjective. On the other hand, if I define f as 0A, 1A, and then also 2A, then it is neither injective nor surjective. All right. Well, we got 40 seconds to spare, and you now know everything you need to know to do the homework. Yes, it's not a problem because the 0, 1 can only go to the first element of the two tuple. The 1, 2 can only go to the second element of the two tuple. So it's not a problem. Exactly the same rule. These rules do not care about whether the domain and the codomain share elements or not. All right. So we are out. We are completely done with today's lecture. The homework is assigned. You have 1 week to work on it, which means if you're really kind of not sure about this stuff, read all the questions, okay? And then try to kind of get some clarification. You can work on it. You can read the content and try to kind of think about it. You can ask the TA, the GPT TA about it. You can also come talk to me about it. Okay, so hopefully we can get some of the clarifications done before Wednesday. Yep. I don't think it will submit the quiz automatically. I'm not sure. Okay, I think there's some people said that it would automatically submit, but only if the tab is active. Because I think it's a JavaScript that does that on the client side. So if you close the tab, there's no JavaScript running anymore. And I don't think the system will automatically say, oh, okay, time's out, and I'm going to submit it for you. So I don't think there's a server side logic to do it. I think that portion is client side. I don't know for sure. I haven't done the experiment. If you suspect that you did not turn in the work, I think you turned in because when I checked, everybody turned in the work already for the homework that was due today. All right, that's it. Okay, I will see you guys on Wednesday. You too.